Hello, my name is Nathan Kroc, and I will be presenting Building a Bridge Between Orthographic and Phonological Processing, where you will learn how our work is bringing machine learning innovation to the reading research space. This work has been a multi-year initiative with guidance and support from many leading education and reading researchers, such as Freddie Hebert from Text Project, Matthew Cooper Borkenhagen from the Florida Center for Reading Research, and Devin Kearns, a Goodnight Distinguished Professor from North Carolina State University. I have had the opportunity to lead the computational modeling efforts, but many of my ideas were shaped by early collaborations with Jay Rickel from the University of Connecticut and Noam Siegelman from Hebrew University, as well as Matt from FCRR. Lastly, as all of you know, academic research can't be done without the tireless efforts of our dedicated and passionate graduate students, so I'd like to extend my gratitude to all of our graduate students from Florida State University's Data Science program. So let's get started. By incorporating technological innovations from the explosive AI research taking place, the work I'm presenting right now, represents state-of-the-art advancements in reading research models. So the goal of the talk is twofold. One, I want to introduce our cognitively inspired multimodal architecture that leverages attention and information bottlenecks to model bidirectional print speech mappings. And then I hope to sell you on the fact that this model provides a more modern and advanced platform for testing theories about reading, development, instruction, and disorders. To communicate this, I will begin by summarizing the relevant historical elements that clearly portray where our work fits into the big picture. Next, we will examine the novelty of our architecture, followed by some very preliminary results suggesting its promise and utility, and then we'll close with some future research directions. So this busy slide provides a bird's eye view of where our work fits into the 40-year dialogue between machine learning and reading research. The intertwined evolution of cognitive psychology and machine learning traces back to a shared 1986 foundation where Rumelhart, Hinton, and Williams popularized the backpropagation algorithm. This breakthrough enabled neural networks to learn internal representations, catalyzing parallel revolutions in both fields. In cognitive science, Rumelhart and McClelland immediately applied the backpropagation to reading research, developing their parallel distributed processing model that very same year. And this marked the beginning of the connectionist modeling revolution. And this work was followed by numerous modeling advances such as the triangle model and the dual route cascaded model, along with their various applications for studying word recognition, dyslexia, semantic integration, etc. Meanwhile, though, Hinton's exploration of neural networks for dyslexia simulations laid groundwork for him for his later pivotal AI contributions, such as the deep belief networks and ALEX network. This was the truly watershed moment giving rise to the deep learning revolution. So what we focus on in this slide is that post-1986, machine learning discoveries have consistently contributed to reading research efforts. So on the right, we see that in 1990, the first recurrent neural network was introduced, but then on the left, we see in 2009, Sibley leveraged the recurrent networks to model sentence processing and syntactic ambiguity in reading. On the right, we see in the machine learning history in magenta that 1997 LSTMs were first introduced by Hochreiter and Schmidhuber, but in 2023, Cooper Borkenhagen employed them in his time-varying model that incorporates temporal dynamics of auditory and visual processing so that he could study learning. So in blue, we see that in 2014, attention was introduced by Bodenau, and this is where we fit in today. So today, we're introducing a new cognitive model built on the foundational breakthroughs of this past 40 years of reading research, but enhanced with the latest breakthroughs in the machine learning space, such as attention, which we're going to focus on today, but also things like gating, fusion, and multimodality. So let's now look at the bridge model itself. We'll start by exploring its multimodality. So for this talk, multimodality really means or modality precisely, refers to distinct sensory channels with dedicated neural pathways for processing specific types of environmental stimuli. Therefore, a multimodal model is a system that processes and integrates fundamentally distinct data types, or modalities, to perform tasks requiring cross-modal understanding. So here we depict them as model input and model output. For example, reading. This is an intrinsically multimodal phenomena where visual information, right, photons hitting the retina, is transduced into auditory information, which are the pressure differentials in the air, like I'm doing right now speaking to you. Spelling, on the other hand, is the process of mapping auditory information that's coming into the ear into motor neural output signals so that we can create or represent visual information. So how does our cognitive architecture model this bidirectional print-speech mapping process? So let's put our sensory icons back in here for reference. And these depict the input and output representations that our model operates on. So let's begin with the phonological processing. Our model consumes and produces phonological information as phonetic vectors. A vector, this vector is simply a collection of features, phonetic features that uniquely characterize every phoneme. And since our phonetic vectors map uniquely to phonemes, for the sake of this talk, let's just represent all of the phonetic input and output as a familiar sequence of phonemes encoded using your favorite system, IPA, SAMPA, ARPABET, etc. Our model consumes and produces orthographic information as a sequence of characters. Each letter is treated independently and is processed internally as a distinct unit of language or information. So how does our model process this information internally? Right, we've talked about how it represents it in the input and output, but now what does it do to it internally? We employ distinct encoders and decoders that communicate through an information bottleneck where the input orthography and phonology are mixed into a single representation. So there's these 5 pieces here, and this modular approach is functionally inspired by known neural circuitry and information processing networks in the brain. For example, the encoders capture the initial encoding of external sensory information into internal neural pathways, which we know takes place in both the visual word form area and the primary auditory cortex. The mixing layer there models the various regions where sensory information is mixed, such as the temporoparietal junction, where auditory, visual, and somatosensory information is integrated, right? And then the decoders there at the end, those capture the functional behavior of mapping the internal neural signals into output, such as what takes place in Broca's area or Exner's area. Each of these modules is implemented with an attention block. Okay, and these are the highly flexible neural network components that are known to adapt to various tasks and are in fact the breakthroughs from 2014 and 2017 that I referenced earlier in the timeline. These are currently powering the AI revolution around us today. So let's walk through an example of how information propagates through the model. To do this, we'll focus on the reading pathway, namely this one here. The orthography to phonology pathway consumes letter-wise representations as an input string, which could contain multiple words, right? So this can be multisyllabic, multi-word, can consume whatever we want as input. 2 is where the model can focus on different parts of the input to complete its task of reading or spelling. This is the attention mechanism at play here. 3 is the bottleneck that affords us a rich space to introspect how the model is actually learning. 4 is where the phonological decoder extracts the phonetic information from the information bottleneck, so it has to learn to map it into a new space or a new representation that's useful for the next piece here, which is the final piece, where the phonetic information is mapped to the actual output phonemes, where it actually produces the pronunciation. So the output is then compared to, say, the target word. For example, we do a little comparison, and relevant information for the model to improve its performance is packaged into a learning signal, which back propagates through the network and updating all the model's weights and its parameters. And this is the key here. This is the process of learning. And we can train various pathways to model numerous learning environments. For example, we could train the phonology to phonology pathway first across the top to simulate language acquisition at home, right? Language comes in, language comes out. After that pre-training, we can then take that same model and train the orthography to phonology pathway as depicted here to see how that learner performs in word naming tasks while we teach it to read. So here we're going to look at some asymptotic performance of the model while it's learning to pronounce some words. So in this data set, or this example, there were 12,000 unique words, and it was exposed to them 150 times. So there's no pre-training here. So this is training a randomly initialized model to read without any background knowledge or information, right? So that pre-training task I mentioned just in the previous slide, that isn't done here, which is why so many exposures are needed. And this shows that the model is capable of learning a large corpus of words and print speech mappings. And we use this as an opportunity to establish numerous hyperparameters in the model, number of time points, number of hidden units in the information bottleneck, etc. So here we can see the model learns. One of the experiments we ran is comparing our model's performance to the Woodcock-Johnson assessment. And so this is the rank correlation between the sequence of items from the WJ3 normed reference assessment and the time points at which the item was first correctly decoded by the model. So in other words, the x-axis is the sequence of acquisition in children that we know from experimentation, and the y-axis is roughly the sequence of acquisition of our model. We see a strong correlation in word reading skill acquisition, suggesting that the model struggles with similar words and in a similar order to humans. These are ELP naming data. A black dot here is a word. So the x-axis is our model's accuracy for that word through training, and the y-axis is the speed with which a human correctly names the word. The correlation between our model's accuracy and the ELPRT here suggests that processing difficulty for our model aligns with processing difficulty with humans. Another experiment that we're going to look at here will examine the learning of the model in context of different print environments. We'll look at decodable and non-decodable texts. To test the network on a number of different relevant training environments, we constructed 5 such environments. The first is an environment of decodable texts from a large decodable text program used widely in the US. Adult words comes from the corpus of randomly sampled words from the Contemporary American English dataset, COCA. Child words comes from a database of randomly sampled children's texts from Lewis et al. 2021. Sampled adult words is a set of frequency sampled words from COCA, and then sampled child words are a set of frequency sampled words from that same Lewis et al. Dataset. Okay, so that's what we're going to look at here, and the results are: the experiment demonstrates how we can manipulate the learner's reading environments to examine the outcomes of these different learning experiences. And these particular results suggest that there's a causal interpretation for us to identify preferred learning environments. Namely, the decodable texts were learned more easily and more quickly than the sampled child words versus the sampled adult words, and then the random words were both the worst. So here's data from a more nuanced experiment that paint a bigger picture than the previous results suggested. So we trained the model in 2 environments, decodable text and common trade books, but we varied the amount of random background vocabulary words, resulting in 4 conditions here. So first, we see the model's accuracy after learning in 100% decodable and 100% trade book environments. However, if we begin to dilute the data set with background vocabulary words, what happens? With 75% decodable and tradebook words, the accuracy decreases. With 50%, the accuracy decreases further, and the gap between decodable and tradebook accuracy shrinks. And this pattern continues, and we see that the benefits of the decodable text environments quickly wash away by uncontrolled background vocabulary exposure. So this concludes this very brief introduction to our bridge model, and I'd like to leave you with this final message. Multimodality is nothing new. In fact, it was the cornerstone of computational reading models since as early as 1989 with the triangle model. However, numerous technical, computational, and mathematical challenges have limited scalability and utility of these models. The tremendous global effort, however, in advancing multimodal AI recently has produced various breakthroughs that have the potential to significantly advance the reading research field. So it is our hope that our work here today is a small step in that direction. Thank you very much for your attention, and please reach out if you have any questions or wish to collaborate in applying this model to your own work.